All right, so let's look at proposition 7 now of book 1, which is another fairly wordy proposition. It says, given two straight lines constructed on a straight line from its extremities, and meeting in a point there cannot be constructed on the same straight line from its extremities, and on the same side of it two other straight lines meeting in another point and equal to the former two respectively, namely each to that which has the same extremity with it, which is a mouthful. Really what it is saying is that if you're given three sides, and assuming a triangle can be created with these three side lengths, it's saying that that triangle is unique. It's not possible for there to be another triangle. Sort of thought of in a different way, maybe a little bit more visually, it's saying that if you look at this line, so assume that, so let's see, just kind of going along with the wording here, it says there cannot be constructed on the same straight line and on the same. So assume that AB is like just some fixed line that's sitting there, and both AC and CB are sort of just like sitting off to the side. And we grab them and we put them together in a way to form this triangle right here. It's saying that this is the only possible triangle that can be formed. And I think that another way of kind of viewing this is to think of it in terms of like circles that were formed. So if we have our initial line AB, and then we make a circle. I'm not going to do it just because it's not part of the proof, and I don't want to muddy up my page too much, but if you imagine making this circle with center A and radius AC, you make one circle there. Then you make another circle with center B and radius BC. You make this circle over here. Then if you were to make those two circles, you would see that, at least on this side of AB, these two circles only intersect in one spot. So that's literally all that it's saying, is that if you're given three side lengths, and kind of this is not, the whole business of whether or not a triangle can actually be formed is not stated in Euclid's formulation, but it's something that you have to think about, because if you take three different lengths of lines, there may or may not be a triangle that could be formed. Right, and I was just thinking, like, the reason that I just paused and you probably could see the gears turning is because I was just thinking about how in trig, with law of sines, we use a really common problem, maybe the most common problem that comes up for law of sines is the side-side angle, the ambiguous case. And I was thinking, wait, is that a counterexample to what I'm saying? No, it's not, because side-side angle, it assumes that you're given two sides and an angle. This is assuming that you're given all three sides. And yeah, this is saying that there is only assuming, and it's not, again, this is the assuming that a triangle can be created is not listed in here, because it's possible that you might be given three side lengths and no triangle can actually be created. Which would have something kind of like ties into this with the triangle inequality that comes up so much in analysis. So in any case, that's what this is saying, is that if you have three side lengths, you can have at most one triangle that can be formed. And if a triangle can be formed, it is a unique triangle. All right, so let's run through the proof, because I think this is sort of a clever proof that he uses. So basically he says, all right, yeah, so assume that we've got our side AB here, and then we've got, I'm just like erasing these little circles. You probably can't even see it on the camera, on the video, but I could see it. It's bugging me. So assume that we've got our side length AB here, and then we've also got AC and CB. They form this triangle. But for the sake of contradiction, let's assume that we also have two side lengths, AD and DB, where AD is equal to, so maybe I'll write this all out. So assume, here's kind of the setup. It's contradiction. So this is by contradiction, by the way. So assume that we have some side length AD equal to AC. We have another side length DB that's equal in length to CB, and basically that you can form with AB and D, you can form another triangle where, so how should I state this in my own terms? Maybe I'll go back to Euclid to see what he says. For, if possible, given two straight lines ACC be constructed on the same line and meeting at C, let there be two other straight lines AD and DB constructed on the same line AB and on the same side of it. So that's kind of like an important nuance. It might seem kind of like implied, but it's an important nuance because you could create technically a second triangle where the point, the vertex of the triangle is down over here. It would be, but it would be the exact same triangle. It's just sort of like flipped over. It's saying assume that we have AD and DB and we can stand AD and DB up on AB in such a way that they touch, they form another triangle, but maybe D falls over here. So D and C are not the same. So assume AD equals AC. I'm just trying to think about how to say this on my own. And assume, maybe, I'm just trying to be a little bit rigorous with this, like kind of in terms of, modern things. Assume that the triangle ABD exists where D does not coincide with the point C. Right, so what would that triangle look like? Well, we can build it, and I think what I'm going to attempt to do is make these lines just slightly fainter. So it's like this is sort of like our little phantom triangle here, just so it doesn't get too complicated. Right. Oh, and of course this one is coming out looking almost like a right triangle. It's fine, it doesn't matter. I have this weird thing where, like, I have to try very hard to, when I'm making triangles, I have to try very hard to not make them right triangles. I don't know why, but whenever I'm making right triangles, they either come out equilateral or they come out right triangles, or like, isosceles. It's hard for me to just freehand draw a scalene triangle. I have no idea why. All right, so here's our assumption. Here's our setup. We're assuming that DB is equal in length to CB, and you have to assume, like, okay, well, based off of the picture, that's clearly not the case. But assume that DB equals CB. Assume that AD equals AC, and we're able to form this triangle where D does not coincide with C. Okay, so first things first, Euclid says, all right, so that being the case, construct the line CD. And Euclid doesn't justify this because he's just like, look, man, like, you should know what postulate that's coming from. I'll justify it here today. Maybe next time I won't. But yeah, between any 2 points, we can construct a line. So there's our line, CD. And what reasoning does Euclid use? It's pretty clever, I think. All right, so he says, all right, well, then this being the case, we have this new triangle right here, this triangle ACD, and we know that AD is equal to AC. So since AD equals AC, in other words, since ADC is an isosceles triangle, we know that from proposition 6, right? I believe it was proposition 5 was the one that said if you have equal sides, then the angles at the base are equal. So we know then, since those two sides are equal, we know that the angle ACD equals the angle ADC. So these two angles right here is what we're saying. Those must be equal. And that comes from proposition 5. Euclid, at least in my translation, this is not justified, and that definitely should be justified. I mean, I guess he's just assuming, like, hey, if you've made it to proposition 7, you've read all of the previous propositions, you understand why this is true. Oh, no, I take that back. It looks like it is justified in my book. It's just kind of like off to the side and small. Okay, so ACD equals ADC. Yeah. No biggie. And then let's see here. So then he goes on to say, and this is what Euclid says, and I think that it requires a little bit, or it calls for a little bit more justification. He says, therefore, angle ADC is greater than angle DCB. All right, so what are we looking at? We're looking at angle ADC, so this angle right in here, and we're saying that that must be greater than angle DCB. Well, that makes some sense, right? Intuitively, I think that it should be justified a little bit more, so I'll kind of make a note here. This isn't in the translation, but I'll just kind of note how you can find this inequality. Well, notice that angle ADC is equal to, let's see, ADC is equal to angle ACD, right, sorry, is equal to angle ACD. That's actually where I should start at ACD, because ACD is equal to what? ACD is equal to angle ACB plus angle DCB. Right? So angle ACD, this sort of large angle right here, is really the sum of these two smaller angles, ACB and DCB. Well, if angle ADC is equal to all of this, so angle ADC is equal to ACB plus angle DCB, well, the whole is greater than the parts. So from this, we get that, yeah, angle ADC is, yeah, it's strictly greater. And that's kind of the crux of it, too. It's strictly greater than DCB. All right, I'm just trying to like make my angle, my greater than, less than, different from my angle signs. They look a little bit similar. And then here's kind of the part that sort of makes me laugh a little bit, because after Euclid states this, he says, therefore, angle ADC is greater than DCB. There's the justification. And then he goes immediately into another. He says, well, from that, it follows then that, and here's the wording. I'll write it the way that we would say it, but the wording is funny to me. He says the angle CDB is much greater than the angle DCB. So he says, and this is like just reading it, let me just read the two lines because I think they're kind of funny. He says, therefore, the angle ADC is greater than the angle DCB. Therefore, the angle CDB is much greater than the angle DCB, which I think is just kind of like funny, because it's like, what does that mean? Much greater. Not only is there greater, there's also much greater. So yeah, the foundations of, mathematical rigor they're appearing, but by today's standards, they're definitely lacking. All right, so why is this true? Why is it true that angle CDB is strictly greater than angle DCB? Well, all right, let's look at the diagram. So angle CDB right here, this sort of angle right there, CDB, versus angle DCB. All right. And I'm just going to follow along with my notes rather than sit here and do the thinking on the spot. So the reason is because angle CDB is equal to angle ADC plus angle ADB, right? So CDB right here, CDB is equal to ADC, so this little angle right in here, plus ADC is up here, ADC plus ADB, right? These two angles together form CDB. Yeah. Okay, that checks out. But from this in here, this is saying that, so, right, what am I doing? Oh, just from in here, CDB, right? Just from this, it follows that angle CDB is greater than angle ADC. And we said in the previous step that angle ADC is greater than angle DCB. So this is why it's much greater. It's not just like sort of one step greater. It's kind of like you can think of it as this chain of inequalities. It's sort of two steps greater. It's much greater. There we go. Right, so angle CDB is much greater than angle ADC. But then again, since CB equals DB, right, and this is by assumption that CB is equal to DB, well, if CB and DB are the same, that means that BCD, triangle BCD, is isosceles. And these two angles, angle BCD and angle BDC, are the same. So, since CB equals DB, if I was writing this, I would say, just to make it a little smoother, it follows that angle CDB equals angle DCB. Right? Again, and that's because when you have an isosceles triangle, the angles at the base are the same. So this one is not justified, maybe because it was justified sort of previously on this step right here, but it's proposition 5. And this is a contradiction. So this is a contradiction. Why is it a contradiction? Well, because we're saying on the one hand, the two angles are the same, CDB equals DCB, but also we know that CDB is greater than DCB. So that's the contradiction in there. So again, this is just how I finish off my proofs by contradiction. So our original supposition was wrong. So what's the conclusion? D equals C. They're the same. And that's what we set out to prove, is that, if you set up on this same AB two lines that are equal to AC and CB, then those two lines are going to intersect exactly at C. Okie dokie, therefore, etc.